In this podcast, we're going to talk about disaccharides. We're also going to talk about the three more common disaccharides that you're going to come across in this course, as well as probably just in life in general. And we're also going to talk about how to classify the glycosidic linkage between the monosaccharides that make up a disaccharide. Disaccharides are made up of two monosaccharides. As you remember from our monosaccharides podcast, the monosaccharide can be either 5 carbon rings or 6 carbon rings. There are 3 that I'm going to ask you to have memorized, and they are as follows. The first is maltose. Maltose is found in candy and cereal and malt beer. And maltose is a disaccharide that's made up of 2 glucose monosaccharides. So each of these are glucose. And remember that glucose is one of those monosaccharides that I asked you to already have memorized. So you should be able to, if I were to give you this structure on a test, you should be able to identify that this is glucose and this is glucose, and therefore this is a maltose disaccharide. The next disaccharide you need to know is lactose. Lactose is a milk sugar. It's found in all dairy products. And lactose consists of a glucose molecule, or monosaccharide, and a galactose monosaccharide. Again, you have had to memorize both glucose and galactose. I would anticipate if you're just looking at the monosaccharides that you'd be able to recognize these. And then also know that if you have a glucose and a galactose together, that is in fact lactose. The final disaccharide I need you to have memorized is sucrose. Sucrose is also known as table sugar, and sucrose is made of a glucose monosaccharide and a fructose monosaccharide. And as you can see by the way they bond and by the way we show this disaccharide, this one's really easy to pick out for 2 reasons. First and foremost, we have a link that we've never seen. They're not side by side, they're one on top of the other. And second, this is the only disaccharide I ask you to know that includes a ketohexose in it. So it's pretty easy to pick sucrose out of the crowd. All right, so it's important to note how we form these disaccharides. So what's going to happen is you're going to start off with a hemiacetal of one monosaccharide. So here's our hemiacetal. It has an OR group and it has an OH. So we know it's halfway to an acetal. That's going to react with a hydroxyl group on another monosaccharide. So we're starting with carbon number 1 and carbon number 4. The hemiacetal of one and the alcohol of the other are going to react. We call this a dehydration reaction because we remove a molecule of water from that. So removing the OH on carbon 4 of the second monosaccharide and the H from carbon 1 of the first monosaccharide is going to produce this bond. And if that looks familiar, that's good because it's technically an ether. However, we refer to this as a glycosidic link, and we're going to talk more on the next slide about how to classify those and how to number those as well. All right, so as we talked about on the last slide, the ether bond that's connecting those two monosaccharides is called a glycosidic linkage. And just like your monosaccharides, you can have alpha and beta glycosidic linkages depending on if that ether bond is below the plane of the ring of the monosaccharides or if it is above the plane of the ring. So it's important to note that we are making this linkage between the anomeric carbon on one monosaccharide and the other position does not matter, but we're starting with the anomeric carbon on the first monosaccharide. And so we start numbering around the ring with the anomeric carbon and we go clockwise, 3, 4, 5, 6. This is important because when we describe our glycosidic linkage, we want to say whether it's alpha or beta, and we also want to say what 2 carbons are involved in that glycosidic linkage. We're going to do the same thing for our other monosaccharides. So 1, 2, 3, 4. I'm going to stop counting because that's involved in the bond, and that would be overkill. So notice that this bond is going down or below the plane of the ring. So I would call this an alpha 1,4 glycosidic linkage. Now, your book likes to put the 1,4 first and then the alpha, and your lab manual does it the way I've shown you. Just get the numbers right, get the correct anomer, and you'll be just fine. A beta-glycosidic link is what we would see here in lactose. Again, if we were to classify this, notice that this glycosidic linkage is going above the plane of the first ring. We're looking at the anomeric carbon for the first ring, and it's going above that. So this would be a beta linkage. We are going to again number, and I'm not going to continue numbering because I've already gotten the carbon that's involved in the glycosidic linkage. 3, 4. So this is again a 1,4 glycosidic linkage. This time it is a beta. So notice that in both of these, the alpha and beta is referring to where the OH was on the original monosaccharide. Was it pointing down? Was it pointing up? We do, as we've already practiced, use numbers to designate which ring atoms are joined. And then we have sucrose, and sucrose does not fit this mold. Sucrose is not given an alpha or beta designation, and that has to do with the fact that we are joining 2 anomeric carbons on 2 different monosaccharides. So we are simply just going to describe this in terms of which carbon numbers are joined together. So I'm going to count around the ring. There's 1, I'll stop there. Now, ketohexoses are tricky. Don't forget to start with the tail. This is 1, 2, 3, 4, etc. So this is a 1, 2 glycosidic link. This is also considered a non-reducing sugar, which is something that we have briefly mentioned before, but we'll talk more about in lab. All right, so lactose is something that we come in contact with in our everyday life. It's in every dairy product. It's considered a milk sugar. As we have looked at on the last page, this is a beta 1,4 glycosidic linkage. That's the type of linkage between these 2 monosaccharides. When you drink milk, you have an enzyme called lactase, notice the ASE ending, that breaks apart that 1,4 beta glycosidic linkage between your 2 monosaccharides. However, not all of us still make this enzyme, and therefore some of us are not able to break apart the 2 monosaccharides that make up lactose. So these people have lactose intolerance. And what accompanies that is you're not able to break apart your 2 monosaccharides. You're going to wind up with severe abdominal cramping, diarrhea, gas. It's a mess. So there's one of 2 options that you can do to overcome not having this enzyme present. First is you can drink something like Lactaid. Lactaid does not have lactose in it. It's lactose-free milk, so you don't have the milk sugar. You won't have any of the problems by not having the enzyme to break apart that disaccharide. The second option is to take a pill. You can take a medication that has the enzyme lactase in it right before you drink milk or you eat any dairy products, and that allows for your stomach to have that enzyme in it so you can break apart the glycosidic linkages and enjoy ice cream. We live in a most amazing time. What a time to be alive. So the molecule that you're looking at here is called raffinose. Raffinose is present in broccoli, cabbage, beans. See where this is going? Humans do not have the enzyme necessary to hydrolyze or to break these glycosidic linkages. So what typically happens when you eat beans and broccoli and cabbage is they're going to pass to the large intestine, all the way through the large intestine undigested. And then they're going to sit in the large intestine, and you have bacteria in your large intestine that starts to ferment this cabbage and this broccoli, trying to break it down. Well, when the bacteria is fermenting this broccoli, it produces a lot of gas, which is why when it comes to beans, the more you eat, the more you chew. That is true. So what we have now to combat that is you can take a product such as Gasax or Beano, and that's going to have the enzyme needed to hydrolyze these glycosidic linkages to prevent the fermentation of these foods as they're passing through the large intestine, therefore Prevent gas. What a time to be alive.